All right, welcome to day 3. You should have watched the day 1 and day 2 videos on Edpuzzle for your homework, and then you didn't have to do any of the homework problems. So we're going to jump ahead in our notes packets to the day 3 notes, which starts here. So we're doing derivatives of parametric equations. So if you have a smooth curve, the parametric equation, the x can be determined by some function in terms of t f of t, and y can be determined by some function g of t. Well, if we want to find dy over dx, imagine we multiplied each of these by 1 over dt. Well, now that becomes dy over dt over dx over dt. So we can do our derivative of y with respect to t in our numerator, our derivative of x with respect to t in our denominator, and that will give us the derivative of our parametric function at any value of t. Now we say where dx over dt is not 0 because that would make the derivative undefined. So we're going to see if we can find the slope. A planar curve is often what's said for a parametric equation. Those mean the same thing. So we're going to find the slope of a planar curve at each of those points. Well, first we need to do our derivative. dy over dx is really dy over dt over dx over dt. So our y was 5 sine t. Sine's derivative is cos, so we'll have 5 cos t. X was 5 cos t. Its derivative is negative sine, so we'll have negative 5 sine t. And if we neaten this up, a cos over a sine is a cotangent, and we'd have a negative, so we'll have negative cotangent t. Well, to find our slope, we need to find what value of t we are working with. Well, we have x is 0 and y is 5. So what we do is we set 0 put 0 in for x in our x equation. So we're going to have 0 equals 5 cos t. And again, this is coming from the originals. 5 in for our y equation. So 5 equals 5 sine t. And then we go through and solve each of these and find a common solution. Now, what I mean by a common solution is some of these might have multiple solutions. Say, like a trig function by our ASTC could be in multiple quadrants. Or sometimes you'll have like a square root that could have a plus and minus. So you solve both of them and find where the common solution would be. So if we divide the 5 over, we get 0 is cos t. If we divide the 5 over here, we have 1 is sine t. So we want to think on the unit circle, if we are at the point 0, 1, because cos is the x and sine is the y, 0, 1 would be at pi over 2. So we're going to work when t is equal to pi over 2 to give us our slope. So therefore, our slope at this point, and I guess this work went for the now find t at 0, 5, our slope is just going to be negative cotangent at pi over 2. Well, cos of pi over 2 we have is 0, sine is 1, so negative 1 over 0 is just 0. So our slope for this planar curve or this parametric equation at 0, 5 is just 0. So we're going to do a similar idea in part B. We already know our dy over dt over dx over dt is negative cos t from the first part, so we don't have to redo that. Let's set negative 3 equal to 5 cos t and 4 equal to 5 sine t. And this will allow us to find our value of t. So if we divide 5 over, we'll have negative 3/5 cos t. Divide the 5 over, we have 4/5 sine t. Well, a negative cos and a positive sine means we're in the second quadrant. Our adjacent is negative 3, our hypotenuse is 5, and our opposite is 4. Well, we don't even need to know what that actual angle is. You could say that it's the inverse cos of negative 3/5, or but we can just work with the triangle. So we know our slope is going to be minus whatever. Oh, I wrote cos there. That should be cotangent. I'm sorry. So that should be negative cotangent of t from the previous question here. Sorry about that if that was confusing. So we should have minus whatever our cotangent is. Well, cotangent is just adjacent over opposite. So I'll have minus a negative 3/4, so our slope here is just 3/4. Well, let's see that those slopes would be consistent if we had done these in rectangular form. In the x equation, if we had divided 5 over, we would have had x over 5 is equal to cos t. Divide the 5 over in the y equation, we'd have y over 5 equals sine t. Well, we would use the fact that cos squared t plus sine squared t is equal to 1. So that means we would have x over 5 squared plus y over 5 squared equals 1. Or in other words, x squared over 25 plus y squared over 25 is 1. Or in other words, x squared plus y squared is 25. So that's where that equation is coming from. Okay, if we eliminated the parameter and wrote it in rectangular form. Well, now you do your derivative implicitly. So we have 2x plus 2y times dy over dx. Subtract the 2x over and divide by 2y, and we'll end up with dy over dx is negative x over y. Well, the slope at 0, 5 now is just 0 over 5, which is 0. That's consistent with what we got before. And our slope at negative 3, 4 will be minus a negative 3 over 4, which is just 3/4. So those are both consistent with what we got when we did it as a parametric derivative. All right, let's try a new example. Same type of thing. We want to find the slope of this parametric or planar curve at 2, 3. So we're going to have to do dy over dx, which is really dy over dt over dx over dt. If we imagine we distribute that 1/4, this is really 1/4 t squared minus 1. So we're going to have 1/2 t for the dy over dt. For the dx over dt, we're going to have 1/2 t to the negative 1/2. Well, the halves divide out, and when you subtract your exponents, we just get t to the 3/2. Well, let's sub in our point to our original equations to try and find the value of t. We're going to have 2 equals square root of t, and we're going to have 3 equals 1/4 t squared minus 4. Well, in this second equation, multiply the 4 over, so you got 12 equals t squared minus 4. Add the 4 over, you get 16 equals t squared, and t is then equal to plus or minus 4 when we take the square root. Well, to decide which one it should be, look at the other equation now. Square both sides, and you get 4 is equal to t. So the common solution is when t is equal to 4, so that's what we should use. So if we do that, our slope is really 4 to the 3/2. So our slope, square root of 4 is 2, 2 to the 3rd is 8, so our slope is just 8. Working with these same curves and this same point, we're going to see if we can determine if we are concave up or concave down at that point. Well, concavity comes from the second derivative. So really this is saying we need to know is the second derivative positive or negative. Now this is where you need to be a little careful because the second derivative is not what you would probably guess it would be. So if we want to do the second derivative, d2y over dx squared, that's coming from that we did d over dx of dy over dx. But we have things in terms of t's. So you would have to multiply this just like we did in the original derivative by 1 over dt for each of them. Well, notice what this now says. We're going to take our first derivative and do it with another derivative with respect to time. But then it gets divided by dx over dt. So just as a refresher from what we had in the previous one, we had that dy over dt from this here was 1/2 t. We had dx over dt was 1/2 t to the negative 1/2. And we had that our dy over dx was just t to the 3/2. So if we want to do our second derivative, oops. Our second derivative, again in these boxes in the blue, is saying do your dy over dx derivative with respect to t, but then it has to be divided by whatever dx over dt was. So we'll take our dy over dx here, do the derivative with respect to t, that's 3/2 t to the 1/2. But then we've got to divide it by the dx over dt. So we'll bring that down, we've got 1/2 t to the negative 1/2. I forgot my negative there. Well, if we neaten that up, our coefficient's going to be 3. Subtract your exponents, and you just get t. So be very careful of that. The second derivative of your parametric, you're not just doing the first derivative with respect to t. It's the first derivative with respect to t divided by that original dx over dt. Well, we already knew from the previous part that we wanted to look at when t equals 4. So our second derivative when t is equal to 4 would just be 12. So we would be concave up, since d2y over dx squared is positive. Well, another thing you look at with parametrics and their derivatives is we'll want to find the speed. So our originals would be the position. Well, the speed of the object would be its change in position over time. So we already found our derivative at this point to be 8. That was dy over dx. However, 8 is not a speed because there's no time unit in it. The y and the x were both positions. So that's representing the change in the y's position as there's the change in the x's position. There's no time in there at all. So if we flip to the next page, if we know dy over dx is 8, what can we do to find the speed? Well, let's think about some things that we know. We knew that dx over dt, that was that 1/2 t to the minus 1/2. And we knew that dy over dt at our point was the 1/2 t. That was from part A. Well, we were working with t equals 4. So if we put in 4 to each of those, 4 times 1/2 is going to be 2. So that means our y units are changing 2 units each second. And the reason that's units per second is because it's a dy over dt. When we put 4 in for dx over dt, we should get a 4th units per second. Well, if the bottom's changing at a 4th units per second, the vertical is changing at 2 units per second. This hypotenuse is the actual change in units per second when we consider both directions. So we've just got to do a Pythagorean theorem. So we'll call that C. We'll say C is the square root of 1/4 squared plus 2 squared. Well, that means c is the square root of 1/16 plus 4. So that means it's equal to the square root of 65 sixteenths. Or in other words, the square root of 65 over 4, not under the square root. So that means our speed at that instant is square root of 65/4 units per second. Because when we did that Pythagorean theorem, we did it with values that had a per some time. So the shortcut way you see at the bottom is, notice our speed is just the square root of our dx over dt squared plus our dy over dt squared. And then what we do is we just fill in for t the time that we're looking at. We had already filled in the 4s, that's why we already had those. So just one more example just to wrap your head around it. So if we said our x position was given by 5t and the y was always 1. So what that's meaning is the y is staying at the same horizontal value, and we're just going to be moving to the right as t goes on. And you have kind of a picture of it there. So your dx over dt would be 5, and your dy over dt would equal 0. So therefore dy over dx, which is our dy over dt over our dx over dt, would be 0. But it's pretty clear from the picture that our speed should not be 0 because we're moving. At any of those times, we're moving to the right. So this is just to show that, okay, yeah, dy over dx definitely isn't the speed, because in this scenario, it's pretty easy to see that we should be moving to the right the whole time. Now, where we could get that speed from is, remember, our speed, using the equation above, is the square root of our dx over dt squared plus our dy over dt squared. Now, technically, those would need the specific time subbed in that you're working with, but both of those are constants, so it doesn't matter in this case. So we'd have square root of 25, which is just 5 units per second. All right, so we got new equations now for x and y. So we want to find the slope of it at t equals 2.5. So our dx over dt is just going to be 1 minus 2 cos t. And our dy over dt is going to equal positive 2 sine t. So therefore, our dy over our dx is just going to be 2 sine t over 1 minus cos t. Well, the other ones we did before gave us a point, and we had to sub those points in for x and y and then solve for t. This one directly told us what we wanted t to be. So we'll have dy over dx is equal to 2 sine of 2.5 over 1 minus cos of 2.5. And we'll pause for a second. Go ahead, punch those in your calculator. And notice it wants you to round to 3 decimal places. Make sure you're in radians when you're doing that. So we should have gotten that was 0.460. On the bottom, we got the same function we want to do at 2.5 again, and we want to find the speed. Well, our speed is just the square root of our dx over dt squared plus our dy over dt squared with that time filled in. So dx over dt, we had 1 minus 2 cos of 2.5. And the dy over dt, we had 2 sine of 2.5. So we'll give you a moment, punch that in your calculator, and round this to 3 decimal places again. So this is 2.864 for our speed. And that would be, this would be units per second for our label. All right, and our last one for this video, when/where is the curve horizontal? So let's find the when first. Well, let's take our derivative that we had. We had dy over dx was equal to 2 sine t over 1 minus 2 cos t. You have a horizontal, when the curve is horizontal, the derivative is equal to 0. So we would want the top to equal 0. So we're going to have 0 equals 2 sine t, or in other words, sine t equals 0. So that's going to be when t is equal to 0, pi, 2 pi. We're going just 0 to 2 pi. Now, if we wanted to know vertical, we would want an undefined slope. So then we would want our denominator, which is the dx over dt, to equal 0. So that's our answer to the when. For the where, well, let's put 0 into our original function. 0 minus 2 sine of 0 is 0. Cos is 0 at 1, so that'll be 2 minus 2 is 0. So 0, 0 is a spot. When we put pi in, all of these actually are going to give zeros for the sine. So for the x value, it's just going to be whatever we put in for t. So we'll have pi, comma, cos of pi is negative 1. So we'll end up with 4 there. And then, like we said, it would just be 2 pi for the x. Cos of 2 pi is 1. So then we are back to 0 again. And just note on our scale here, so here's that 0, 0. This is going by halves. So that pi 4, and I'm not even sure what our scale is down there because we're going by 14, but there's the pi comma 4, and then here's back to the 2 pi comma 0. That's it for this video. Have a great rest of your day.